Now we're continuing to talk about crystalline solids. Crystalline solids can be divided into three categories based on what the individual particles are. So molecular solids are crystalline solids where the individual pieces are molecules. Ionic solids, the individual parts of the lattice are ions. And then atomic solids are composed of atoms, not molecules or ions. Atomic solids are subdivided into three more categories: non-bonding, metallic, and network covalent. And we'll talk about each of these individually. So molecular solids. Examples are solid water, ice, and dry ice, which is solid CO2. We have individual molecules, covalently bonded atoms, discrete molecules that are in the solid form. What's holding them together in the solid form are intermolecular forces. Intermolecular forces are weak, and so molecular solids tend to have low melting points, low up to moderately low melting points. Here's an example of two different molecular compounds, and they would form molecular solids, benzene and toluene, and they have low melting points. Molecular solids, some of them can crystallize in different structures, and these are called polymorphs. Poly meaning many, morph referring to shape, so many shapes. The different polymorphs are going to have slightly different properties. They'll probably have different melting points, may have different solubilities, they will definitely have different densities. This idea is really important in pharmaceuticals because some polymorphs have excellent biological activity, whereas another polymorph may have no activity at all. And so which polymorph you have is really important. I think this is an interesting sidebar that was in your textbook talking about chocolate. So the main component of chocolate is cocoa butter, which is a type of a fat, but those are molecules. And it turns out, I learned something reading through this. This was not in the previous version of the textbook. There are actually 6 different polymorphs of cocoa butter. And here you see a picture of 2 different types. This is a lesser quality chocolate, and the reason it's got that whitish color on it, that's called bloom. It's generally not desirable. It's not harmful or anything, but it will look yucky. And this is a higher quality chocolate that's nice and smooth looking. The melting points of these different polymorphs are different. So the lower quality chocolate will melt at much lower temperatures, 17.3 degrees Celsius. That's below room temperature. It's going to be melty. Up to 36, which is just below body temperature. So that's just barely going to melt in your mouth. The most desirable is this one, number 5 at 33.8. And so making chocolate is actually, it is chemistry, and it can be very finicky, right? You can't just like slapdash do it. It's like a tricky experiment. So what they do is they take the chocolate and they melt it, and they get all the forms to be melted. So now we've got liquid, and then you let it cool down a little bit. As it cools down, the different crystalline structures begin to form. If you let it cool down all the way, you're going to have a mixture of them, and you're going to have low-quality chocolate. So they let it cool down a little bit, and then they heat it up again. So they cool it down so that at least some of this polymorph 5 has started to form. Then they warm it up again so that all of these lesser forms melt. But they have crystals of this polymorph 5 present, and then they let it cool slowly, and those act as nucleation sites for the crystallization of the formation of the solid. And what happens as solids form is if there's an existing crystal there, they will tend to attach to that and form the same type of crystal. And so you can coax the chocolate into going into a single polymorph, a more desirable one. So I thought that was interesting. I like chocolate. Ionic solids, we're going to talk a lot more about these in another section. These are solids whose composite units are ions. So these are any ionic compound is going to be an ionic solid. Examples are sodium chloride and calcium fluoride. What holds these together are the ionic bonds between the cations and the anions. Those bonds are very, very strong. So unlike the molecular solids, ionic solids are going to have really high melting points because you have to break the ionic bonds to get them to melt. Atomic solids. Examples would be things like xenon, iron, silicon dioxide. We'll talk a lot more about this one later. You might think that that would be a molecular solid, right? There's two different elements here. It looks like a molecule. It's actually not, though. It's not discrete molecules. It is individual atoms. And so I'll explain that later. For non-bonding atomic solids, we just have individual atoms held together by dispersion forces. There aren't any dipole forces or hydrogen bonding because there's no polarity involved. It's just individual atoms. These are going to form closest packed structures, either hexagonal closest packed or the face-centered cubic. And that's to maximize the coordination number, minimize the distance between the atoms. They're going to have very low melting points because the only thing holding them together are dispersion forces. The only examples we have of this type of atomic solids are the noble gases in their solid form. So not many examples of this. And just for reference, argon melts at minus 189 and xenon melts at minus 112 degrees Celsius. The melting points are going to vary with the molar mass. The higher the molar mass, the higher the melting point, but all of them really, really low. Metallic atomic solids, these are elemental metals. So anything that's a metal up there is going to form a metallic atomic solid. Held together by metallic bonds. This is the electron C model where you have ions of the individual metal atoms. They are ions because they've let one or more of their electrons go out to play in the neighborhood. And so these electrons are held very, very loosely and they can move around. But this sea of electrons is what holds all these different metal ions together. Metals also form closest packed structures. The bonds here are non-directional, and so they're going to have attraction in all directions, and they will naturally form closest packed structures. The melting points are going to vary because the strengths of the metallic bonds vary. So some metals have very high melting points. Others, like mercury, have low melting points. Mercury is a liquid at room temperature. And then there are network covalent atomic solids. These are atomic solids. They are composed of atoms, but the atoms are actually covalently bonded to each other. Examples are diamond, graphite, and silicon dioxide. The crystal structure here is not closest packed because the atoms are bonding together, and so they're going to be limited in the geometry by the types of hybrid orbitals they form. So we see a lot of tetrahedral geometry here because things like carbon and silicon like to form 4 bonds, and so they have that tetrahedral shape. These have very high melting points because covalent bonds are very strong. Okay, so what type of an atomic solid is gold? Don't overthink this. Metal, metallic, yeah. Oh, yeah, sorry about that. It's a metallic atomic solid. It's a metal. Anything that's a metal is a metallic atomic solid. Looking at these 3 compounds, which would you expect to have the highest melting point? We're thinking about what kind of solids are these? What's holding the particles together? Well, krypton is this atomic, ionic, or molecular? Atomic. It's just an atom. It's an element. So that's atomic. And what kind of intermolecular forces hold that together? Dispersion forces. So that's only got dispersion forces. What kind of a solid is iodine, I2? It's going to be molecular solid. What's holding it together? Dispersion forces. It's nonpolar. What kind of a solid is this? Ionic, right? What's holding that together?
Dispersion and dipole.
No. Dispersion forces, dipole forces are intermolecular forces. Does this have molecules? No. An ionic substance has ionic bonds. Okay, so this is held together by ionic bonds. Which are stronger, ionic bonds or dispersion forces? Ionic bonds are far stronger. Okay, so this is going to have the highest melting point. This isn't something that you can just memorize a list of. You have to be able to look at stuff like that and think about it. I know that's not fun for some people. Any questions?